Okay, so the purpose of this lecture, as I mentioned, I want to minimize the amount of electromagnetics I teach in this course and concentrate on the algorithm it takes to model and simulate electromagnetic things. However, unfortunately, to really appreciate how the methods are working, there's some electromagnetic tidbits that you all need to be aware of in concept. So that's the purpose of this lecture. It's not really to review electromagnetics. It's the specific tidbits that are going to be useful to you for modeling stuff. So what is particularly important in my mind is right here. So polarization. We need to understand what we mean by linear, circular, kind of how it's quantified, because we're going to build a device into our model, and then we're going to have to define what kind of wave is going to hit this thing. So we need to understand the polarization stuff so we can design our source correctly. Then there's also this concept of wave vectors, and this concept is throughout and gets a lot deeper as we delve into this course. In fact, there's going to be another whole couple lectures that goes into using that for weird things. But so we'll start shallow here and we'll get deeper as the semester goes on. We'll talk about something called index ellipsoids, which is the start of actually some pretty cool stuff. Then we're going to talk about electromagnetic behavior at an interface, and I really want to give you an intuitive feel of what's actually happening with the field when a wave hits an interface. For two reasons. That's going to give you some insight of what's happening in our models, and you'll see how we connect those dots later on. But given those equations, it also gives you a great way to benchmark your codes. If you can calculate reflection for a certain polarization, certain angle of incidence, then you can go to your method and hopefully it predicts exactly that. So it's great for benchmarking. And then real quick, we'll touch on something called image theory and then lenses. And these are all the little electromagnetic tidbits that pop up the most often in my mind. Everybody ready? Polarization. So polarization, we got a wave trucking along. And we define polarization in terms of the electric field. So we ignore the magnetic field. And really, whatever the electric field is doing, that defines our polarization. If it is oscillating just up and down in a straight line, we call that a linear polarization. It'll corkscrew, we call that a circular polarization. And it can actually trace out ellipses, which is everything else. We call that elliptical polarization. But it's defined in terms of the electric field. So you don't look at the magnetic field to interpret anything about polarization. It's the electric field only. I robbed these from Google, I think. So unfortunately, there's actually two ways to define polarization. If you are an electrical engineer, there is this convention, and we define polarization from the perspective of the source. So it's kind of like your eyeball sitting here at the source and you're watching the wave move away from you. If you're an optics person, then you tend to review it from the receiver. So your eyeball's over here looking in towards the wave. The wave's coming at you. And so left and right-handedness actually changes depending which way you're looking. And I do both. So I end up completely confused when somebody says right-hand circular. I don't know what that means anymore because there really is two definitions. I think in this course we're going to stick with the more electrical IEEE definition because we're all electrical engineers. So our eyeballs are at the source and the electric field is going to be tracing out a circle, and depending which way it's moving, if you're looking at the source, or from the source, you're going to see that it's corkscrewing. When it comes up to the top, it's going to the right. I'm going to play with that for a bit. So it's right-hand circular. Left-hand circular does the opposite. So we'll stick with what's on the left-hand side. But I'll warn you, if you're reading literature, just be cautious of this, that somebody might just throw out a particular right or left-hand circular, and don't be real confident you know what that is. Does that make sense? You're watching the electric field corkscrew. So to put math behind it, we will start with linear polarization. And the way we express this is we have an exponential term that's responsible for the oscillations. So that's what's describing your wave. The amplitude, if you will, is a vector, and we're going to call that the polarization vector. So somewhere at the beginning of your codes or wherever you're defining your source, we're going to calculate a polarization vector. So that's the direction the E field is pointing as it's propagating. And the E field is going to be perpendicular to the direction the wave is going, right? So if the wave's trucking along this way, the E field's going to be out here. Trucks along this way. It never, I shouldn't say it never does, but when we're defining a source in standard materials, we're always at 90 degrees. So the way we could define our polarization is giving some angle, because we can be linearly polarized up and down, left and right, or at some angle, as long as it's always oscillating in a plane, and we can put that at any angle theta. So that equation P is calculated at any angle theta. The key thing for linear is that the two components of polarization are in phase. And it may only have one, it may only have X, may only have Y, but they're in phase. So that's why the electric field always oscillates in a straight line. Everybody good with that? Okay, here's the math behind the circular. Notice we're writing it the same exact way. We have a polarization multiplying the exponential. That's cool because we just calculate P a different way, and suddenly we can go from linear to circular or whatever we want. So no matter what the polarization is, you can always come up with some P to give you that polarization. The trick to circular polarization is that it has two components. They're equal in amplitude and 90 degrees out of phase. And depending whether it's positive 90 degrees or negative 90 degrees, gives you right or left-hand circular. But they're 90 degrees out of phase. Everybody good with that? Okay. Then, of course, the elliptical is everything else that doesn't fit to either one of those two. Anyway, this is just a little table summarizing all the different polarizations and how you define the angles. As we delve more into the sources for the algorithms, we'll talk more about this. Everybody comfortable moving on? Okay. Let me move this little box out of the way. So if we take two linearly polarized waves and add them together, we get another linearly polarized wave. And in this case, if we add something linearly polarized in X with something linearly polarized in Y, that means the electric field is actually oscillating in both directions. And so if we add it up, we're really oscillating along the diagonal. But no matter what, if we add two linear polarizations, we get another linear polarization, as long as they are in phase. So this is useful because if I ask you to illuminate something with a polarization at an angle, you're only going to have access to X, Y, and Z, so you're going to have to give it a little component in X and a little component in Y, for example. So you'll need to know that. If I take those two same linear polarizations, but I give them a 90-degree phase shift by multiplying by J, now we get circular polarization. So I could actually make an argument that there is no such thing as circularly polarized waves. All there is just two linears that are 90 degrees out of phase. And in my opinion, that's actually the better way to think about it, that there is no such thing as circular. There's only two linear polarizations 90 degrees out of phase. So think what happens. You got two linear polarizations. If they're in phase, we get oscillation at the diagonal. If they're out of phase, then as you move along, you can imagine the electrical vector rotating, because at first it has to be pointing up and down as the wave trucks along, then it's pointing over this way as it keeps going, and then it's turning. So circular polarization is two linears 90 degrees out of phase. And in my mind, it's actually going to be beneficial to you to pretend circular doesn't exist. Just two linears 90 degrees out of phase. Everybody good with that? If I add two circular polarizations, I get a linear polarization back. So right plus left gives me a linear polarization. And the interesting thing there is, if I take the right and left and I phase shift them, we still get linear, but it actually rotates the orientation of the linear. That's kind of interesting too. When you start talking about things like optical activity and polarization and rotation, this is part of the explanation of why that works. We're not going to get into that. I just want you aware if you add two circulars, you get linear back again. Everybody good? Okay. So why is polarization important? Particularly at the scale we're modeling things, where the device is on the order of the wavelength, things change with polarization. It'll behave one way with one polarization and completely different with the other polarization. So no other reason that makes it important. Also, if we have two waves coming together, interference, as you're going to see, becomes very useful. But if they're orthogonally polarized, so one's polarized one way, the other's polarized another, they're not going to interfere with each other. They're just going to pass through and nothing interesting is going to happen. So in terms of using interference to do things, polarization is very important. So that's the story. So it is important, particularly at our scale. When the device becomes many thousands of times the size of the wavelength, like lenses for optics, then you can actually ignore polarization pretty accurately. But at our scale, we're going to need it. So there's this thing called a Plonker sphere. And think of it like the Earth. Around the equator, we're going to map all the possible linear polarizations. So maybe we'll start out at 0 degrees linear polarization. If we go around a quarter of the circle, now we're polarized at a 45-degree angle. If we go around the opposite side of the circle, it's 90 degrees rotated. And that'll be 135 degrees rotated, right? And then back to 0. So you can think of the polarization rotating and doing a 360 as it goes all the way around. So we can map any linear polarization to some point on the equator of that sphere. Does that make sense? Then the right and left-hand circular polarizations we'll put at the north and the south poles. And any other point on the sphere is an elliptically polarized wave. Now the reason this is useful is given two strange elliptical polarizations, oh my gosh, are they orthogonal? If you're at opposite sides of the Plonker sphere, you're orthogonal, and it won't produce interference. So it's a good visual tool to envision polarization. So, and I think one of the chapters I forwarded you, chapter 4, Belenas talks about it a little bit better. I like this picture better than anything he provided, but he does talk about it and uses of it. Everybody good? Okay. So very often people talk about waves being polarized either TE or TM. And the thing to remember, when you hear TE and TM, that means there's a device involved. It doesn't make sense to just have a wave out in outer space and say it's TE or TM polarized. That doesn't make sense. There's got to be a device. And so when a wave hits a device, it comes in at some arbitrary angle, right, and it hits. So this vector describing the direction of the wave and the surface defines a plane. So we call that the plane of incidence. We can decompose the polarization into a component that's in the plane and a component that's sticking out 90 degrees to the plane. So the component that's sticking out 90 degrees to the plane we'll call TE polarization, sometimes called perpendicular because it's perpendicular to that plane of incidence, or sometimes called S. And the other one we call TM. But remember, when you hear TE and TM, we're talking about a device. There has to be a device involved because it's relative to that. And the reason these are useful, it just turns out that the electromagnetics decouples into those two modes and they behave differently. So that's why we have the two modes, because when we analyze things, we tend to analyze them separately. Sometimes there's some tricks we can do to analyze them both at the same time with the same model. We can use a circularly polarized wave. So we're actually exciting with both polarizations, and in the end, sometimes we can separate those two answers. So in one simulation, we actually have done two for free, which which is why I talked about adding two linears, and it's a little bit easier to understand why you can do that. So does that make sense with TE and TM? Okay, this gets a little bit crazy. So somewhere in your code, we're going to have to calculate this polarization vector. And it's not quite as straightforward as it seems, and everything's summarized here. The first thing we're going to want to do is calculate a wave vector. And we're actually going to talk a bit more about what that is in a little bit. But suffice to say, it's a vector pointing in the direction that the wave is going. So that's this k-inc. That's the incident wave vector. And as we'll discover, that has two pieces of information in it: the direction of the wave and the magnitude conveys the wavelength. We don't need to talk about that now, but here's how you calculate it. So here's the magnitude of it and the three components. So here would be the x component, the y component, and the z component, based on theta and phi. Theta is the elevation angle of the wave coming in. Phi is the radial angle. So when phi is 0, it only has an x component. There's no y component. And you can see that how it's oriented here. So we have an incident wave vector. That has to be given. So you'll come up with that in the beginning. I'll probably say the angle of incidence and the radial angle, and that's theta and phi. The next thing you'll need is the surface normal. So that's this n. So that's just a vector pointing straight up from the surface. Given those, the rest of this is pretty easy to do. The first thing I like to do is calculate a unit vector in the direction of the TE polarization. So we want something sticking out of that plane. Well, there's a plane defined by the incident wave vector, k, and the surface normal. We have two vectors and they define a plane. That's the plane of incidence, right? So if we want a vector perpendicular to that, that's a cross product. If we take a cross product of k and the surface normal, we get a vector that's perpendicular. We can't trust its magnitude yet, so what we need to do is take the cross product and then divide by the magnitude of that cross product. That gives us a unit vector in the direction of the TE wave. Now there is a problem. At normal incidence, the direction of k and the surface normal are the same, and the cross product is going to be 0, and so that answer would be garbage. So for normal incidence, you can just pick whether it should be polarized in x or y. It doesn't matter because they're going to behave the same anyway. Does that make sense?
Say that again.
So at normal incidence, the k vector and the surface normal are parallel, so the cross product is 0. So in other words, that bottom equation here, we can't use this for normal incidence because it's going to be 0 divided by 0, and your computer will melt. So for normal incidence, you can pick x or y there to be your TE polarization. And since there is no angle of incidence, TE and TM end up behaving the same. They're really the same thing. So you're free to pick either one. Once you have that, so now we've calculated a unit vector this way, and we know our k vector. We can take the cross product again to calculate a unit vector in the TM direction. So that's this cross product. Of course, we divide by the magnitude, so we get a unit vector out again. These cross products are being polluted by the magnitude of the k vectors. We just want to throw that out. That's what's happening. So now we have unit vectors in the TE and TM direction. So our final equation here, the composite polarization vector, is whatever amplitude we choose for the TE polarization times that unit vector, plus whatever amplitude we have for the TM polarization times that unit vector. And so whatever P ends up being, that's the composite polarization vector. We can do linear with it, we can do circular, elliptical, whatever there is. So the TM, the TE, and the K vector, they're all at 90 degrees with respect to each other. So one thing you can conclude, if polarization is restricted to a plane, there's only ever two possible polarization states, right? X or Y in this case. I'll mention as an aside, in some crazy materials, there is actually a third polarization state. I'm not going to talk about that here, but it's kind of neat that that might exist. Okay, everybody good with that? You feel like you could calculate that polarization? Or at least we're going to make MATLAB calculate it, not you. Okay, now let's talk about wave vectors. So it's a vector, and the wave vector simultaneously carries two pieces of information. The orientation of it, or its direction, conveys the direction of the wave. So if the wave is trucking along this way, then your wave fronts are going to form planes this way, right? So wave fronts will be in these planes. The K vector is going to be this because the wave is trucking along left to right. So that's what the direction indicates. The magnitude, the wave has a period we'll call wavelength, the period that it repeats. 2 pi divided by that period is the magnitude of the K vector. So the two pieces of information that it conveys is direction of the wave and the period. And it's not directly period, it's 2 pi divided by the period. Now, I should add an animation of this at some point. Let me actually make a note to do that. On slide 17. My red pen doesn't work. I just bought that. There it goes. So, out in outer space, waves trucking along, and it has a certain period, right? As soon as it enters a material, the wave slows down. And so it's trucking along, and all of a sudden it slows down, and the wavelength gets compressed. So inside a material, your wavelength is actually shorter because the wave slows down, and those wave fronts get compressed. The wave speeds up, it expands again. So the constant here is frequency. That's always the same. Unless you're in a nonlinear material, then we're not talking about that right now. So in a linear material, which almost everything is, it enters, the frequency stays the same, but the wavelength is always changing around depending what speed the wave is traveling. So we can write the K vector in terms of 2 pi over whatever the wavelength is, and it's changing in different materials. Or we can write it this way. We can say 2 pi divided by the free space wavelength, which is a constant, because that's an outer space, just one material. And then we would add the refractive index here. So in other words, if you know the frequency of the wave, then you know its free space wavelength, and the magnitude of K really conveys refractive index, which is a very useful thing. The other thing is the notation of just using lambda without the little not subscript. I hate that, and you'll rarely see me use that, because in some cases lambda without any kind of subscript means whatever the wavelength is inside whatever material you're in. Other texts and sources use that as the free space wavelength, and those are kind of two different things. So I use lambda with the not notation to mean the free space wavelength, and I'll never use just lambda alone. I'll put refractive index in there if I want to convey that it's shorter or longer or something. So just the lambda alone is a very ambiguous thing, because I never know what people are talking about. Is that the free space wavelength or the wavelength inside the material? And I see both, and it's just confusing. So if the frequency is known, free space wavelength is known, and the magnitude of K conveys refractive index, multiplied by that 2 pi over lambda, but that's just a constant. So when we get to index ellipsoids, we're going to come back to that, and we're really going to think of the magnitude of K as being the refractive index, scaled by a constant. So does that make sense? K, two things, direction of the wave, and 2 pi over the period of the wave, or also refractive index. If it goes into a high index material, the wave gets compressed and the magnitude of K goes up, because it's in a higher refractive index material. Remember, refractive index is that ratio by which the wave slows down. Refractive index is 2, the wave's going half the speed of light side the thing. Okay, everybody good? Awesome. Well, the wave vector can be a complex number in the frequency domain. So what on earth does that mean? So here is the equation for our plane wave, and we have this e to the jkz, where k can be a complex number. So we're going to write k as a k prime, meaning the real part, plus jk double prime being the imaginary part. So if we plug that back in here, substitute that in, and then expand out that exponential, what we see is two terms arise. One has a jkz, so the real part of k is responsible for oscillation. That's our phasor. The other one, the imaginary part, had a j sitting there, so this j multiplies this j, and we end up getting just a negative without any j. So what we can see is that's decay, right? Or growth if there's gain. So the imaginary part of k is exclusively responsible for decay, and the real part of k is exclusively responsible for oscillation, being a wave. Everybody good? Two other terms that are used a lot are alpha and beta. You'll see me use beta a lot. Beta is called the propagation constant. And I put those backwards, didn't I? Yes, I did. I labeled them backwards. So we will write a wave this way in terms of alpha. Alpha is an attenuation term, so it's responsible for decay. Despite the fact that I labeled it oscillation, it means decay. And then the beta term, e to the j beta z, is propagation, so I should have labeled oscillation there. So in other words, this alpha and beta are exactly the same thing as the real and imaginary parts of k. And in fact, we could write k this way, as beta plus j alpha, and it's the same thing. Beta is our propagation constant. It's responsible for waves. Its magnitude is 2 pi over the wavelength. And then alpha is pure attenuation. Okay. Everybody good? You guys are machines. Okay, so what does this mean? If we have a purely real k, that means we only have the oscillation term. The decay term's not there. So I'm drawing a wave here that's just oscillating and not changing, and it's trucking along in the direction of k, which is the black arrow. If it's purely imaginary, there is no real part. That means your field is purely decaying. There's going to be no oscillations, no humps. So the second diagram that just shows a decay, an exponential decay. Well, in general, and I would actually argue always, it's actually complex. So we get oscillation plus some decay. All real materials have some loss. It may be really low, and it's a good approximation to ignore the loss, but there's always some kind of loss. When there's oscillation, that's what it takes to push energy. If it's decaying, there's no energy push. And so those types of fields can't push energy. There is one exception to that. We'll probably get into it at some point today. That's called tunneling. And it's the only example I can think of where a purely decaying field can contribute to pushing energy. And we'll get to that in a bit. So those are the three things that your K can do, depending whether it's real, imaginary, or complex. Does that make sense? Well, the K is a vector, in fact. And so it can be two-dimensional or three-dimensional. I'm not going to draw the three-dimensional things, but here's an array of what happens in 2 dimensions. So if both the x and y components of K are both real, then there's just pure oscillation in x, pure oscillation in y. If you add those together, what we get is pure oscillation down the diagonal. Now, let's keep ky real. So we're going to have oscillations in the y direction. But now we have a purely imaginary k. it's going to decay in the x direction. So we have pure decay in the x direction and pure oscillation in the y direction. And this happens all the time. It's a real thing, as you'll see. Okay, pure y, so we're going to have pure oscillation this way, but a complex k. So we actually see it does oscillate in the x direction, thus we see our waves kind of going down the diagonal, but we see this sort of right to left decay in the x direction. Anyway, I don't need to step through the entire matrix, but the x and y components can be different. One can be real, one can be complex, etc., and it will do different things in different directions. Okay, everybody comfortable with that? Probably haven't seen any this kind of stuff before, right? Yeah. Okay, index ellipsoids. This is even crazier. We're going in order of sane to crazy. So there's this thing called a dispersion relation. And we'll have a wave equation. And we have this plane wave solution that we know is a solution. If we plug that back into the wave equation and turn our math crank, out comes some restrictions on what that k vector can be. Because the wave has to follow some rules. It has to follow Maxwell's equations. And so those rules manifest themselves in what we call the dispersion relation. And essentially what this is, it tells you what magnitude k can be depending what direction it's pointing, which is sort of strange. So remember, k kind of implies refractive index. So if we pick a direction, its magnitude will be the refractive index that a wave sees in that particular direction. So for ordinary, easy materials, that's our dispersion relation. And what this says is the magnitude of k is constant no matter what direction it's pointing in. So that's the simplest and most intuitive thing. So a wave in outer space, no matter what direction it's seeing, sees a refractive index of 1, no matter what its direction is. And in fact, in most materials, it's very close to that. So this is also an equation for a sphere. And we can think of constructing a sphere that will call the index ellipsoid as a map of the magnitude of the k vector as a function of direction. So if we connect a point on the origin to a point on the sphere, that's the k vector for that particular direction. A little bit more intuitively, we can think of that sphere as a map of refractive index based on what direction the wave is going. So a wave in outer space, no matter what direction it's going, sees the same refractive index. So it's going to have the same magnitude k. So that index ellipsoid is going to be a sphere. And that's how people get programmed to think. But that's not always the case. So in anisotropic materials, it actually turns out that our index ellipsoids can actually be ellipsoids. That's why we're calling it an ellipsoid. The isotropic is just a special case where it's a sphere. And so we can get crazy things like this inside anisotropic materials. So our k vector starts at the origin and goes to a point on the surface. That's the direction that phase is trying to go. So if you look at waves in an ocean, the lines of the waves, that's phase, and it's trucking along. Energy, and I'm drawing the pointing vector here, energy goes in a direction that's normal to the tangential of this surface. So if we pick a point here, we can define our k vector, but power flows in a direction normal to that surface. Since most materials have spherical index ellipsoids, power and phase go in the same direction. This is actually how we're programmed to think. The direction the wave is going is the direction power is going. But inside something that's anisotropic, and there's other ways of doing this, your surface isn't necessarily circular. So again, we'll connect a point on the origin to a point on the surface. That's the direction phase is trying to go, or phase is going. But actually, power is going in a different direction. They don't have to be the same. In fact, most of the time they're not. They're not too different, but most of the time they're not. It's a special case inside a isotropic material that they're the same. So what on earth does that look like? Well, that's what it looks like. So in the top we have an ordinary material where the direction of the wave and the direction of power is the same, and that's what we're used to seeing. But suddenly this other magical material, the phase or the wave fronts are pointing in a direction different than the actual power is going. So my analogy for this, imagine, we used to call it the Dizzy Izzy. When I was in my fraternity, we had some concept, but anyway, you put a baseball bat down on the ground, you spin around the baseball bat with your head on the bat like 10 or 20 times really fast, and then you would try to run towards something, right? So if my body and my mind wants to run towards a door, that's phase. That's the direction I'm trying to go. The wave fronts are trying to go that way, but unfortunately my body goes off to the side. So inside an anisotropic material, the waves are running the Dizzy Izzy. And so they're not in the same direction. And so I would actually argue in more cases, they are in different directions. But we're always trained to think that everything's linear, homogeneous, isotropic, and power and energy are all in the same direction. But they don't have to be. Everybody good? Okay. Phase matching at an interface. This is going to be really important, for particularly when we calculate how much power is entering and exiting your model. So this is my way of illustrating the wave and the index ellipsoid all at the same time. So the big circle, that's the index ellipsoid. So we're in a nice, well-behaved isotropic material. And I just filled in what the wave looks like on the inside. And so our k vector goes from the origin to a point on the surface. And of course it has an x and a y component. Makes sense? And I filled in the wave. Now, don't get confused, even though maybe it looks kind of similar. This is not the period of the wave. The magnitude of k is 2 pi divided by the period. So don't get confused there. Don't draw the magnitude of k being from here to here, because that's not the case. And so we're restricting ourselves to 2 dimensions. Here's the dispersion relation for a 2-dimensional thing. Does that make sense what I'm trying to convey? I've never seen it drawn anywhere else like this. Okay, so now we have the index ellipsoids with that wave superimposed for 2 different types of materials. On the left, we have something with low index, meaning the wave's trucking along really fast, so the wave is stretched out. But low refractive index means small index ellipsoid, right? So it's kind of an opposite relation. As the index ellipsoid gets smaller, the wave actually gets more stretched out. When we're in something with a higher refractive index, the index ellipsoid is very large, but the wave is very compressed because it's going slower. So it's sort of an opposite relation there. Maybe it's a little bit counterintuitive, but just remember the magnitude of k is 2 pi divided by the period. That's why there's that inverse relation. The bigger the index ellipsoid, the more compressed the wave front. Everybody good with that? Okay. So now it gets a little bit crazy. We're going to talk about phase matching at an interface. So what we have, I can point to here. We have the interface between 2 materials. We have material 1 and material 2. Material 1 has the smaller refractive index here. We're talking about a wave coming down this way and going into material 2. This has the larger refractive index, larger index ellipsoid. But higher refractive index, the wave is more compressed. So the whole trick here, what happens at an interface, is that the boundary conditions require that the function's continuous here. The phase has to be continuous. So the picture immediately above the line has to look like the picture immediately below the line. And so when we have refraction, that's exactly what's happening. It's enforcing that continuity. So one thing I can do, and unfortunately on the recording it's going to lose all this. Okay, so here's a bit of a summary of what we just talked about in sequence. In step 1 here, the wave is traveling pretty darn close to just straight left to right. And that's the fastest we can get the wave to vary in this material. We can always get it to vary slower. In fact, we can at exactly 0 degrees on the other side, it's going to have an infinite period, right? Infinite period in this horizontal direction. Does that make sense what I'm talking about? I feel like I just stumbled over my words. But there's only one magical angle where the spatial periods, if you will, on either side match. And that's why refraction happens.
What happens to the power from one material to the next?
So the power in this case is in the direction of the arrows. So power and K are in the same direction here. If you're talking about phase matching where one of them becomes anisotropic or something crazy, crazy things happen. So I can draw a quick picture of one example. So let's say we're going from a material that has this kind of index ellipsoid to a different material which has an index ellipsoid like that, and that can happen in metamaterials and strange materials. So there's the normal. So we have a wave vector coming in. It has a transverse component which is continuous across the interface. So for convenience, I'll just repeat it over here. Oops, I'm sorry, I threw that wrong. Ends there. And there. Drop a projection down. So that's going to be the direction of phase. Power is now going to suddenly go the other way. We call this negative refraction. Now, very often, people think you have to have a negative refractive index to refract negatively, and it certainly will refract negatively with a negative refractive index, but this does not have a negative refractive index. It's just due to a dispersion thing that has a strange index ellipsoid. That's not even an ellipsoid, it's like a index pincushion or something. But we can refract negatively. And I've seen actually quite a few papers at the time where people were just starting to get into this. They showed that their gizmo had negative refraction. I said, oh, it has a negative refractive index. And it turns out, no, there's two ways to get negative refraction. One's through a negative refractive index, and the other is through the dispersion. So does that answer your question of how you, yeah. Stuff like that is what we'll talk about in the follow-on class. Okay, onward. Now we're going to talk about phase matching. Now we're going from something that has a high refractive index to something that has a low refractive index. High refractive index, big index ellipsoid, but the wave has slowed down and gets compressed. Down here where we have the lower refractive index, smaller index ellipsoid, but the wave is more stretched out. And we can talk about phase matching again. So we have a wave coming in, we have its transverse component which has to be continuous, that's what makes the phase match. And you see we get refraction again, as we would expect. Now, on the right, we're going to come in at a steeper angle. And let's see what happens. Okay, so here's just a quick summary of what we talked about. And here's the one case where we can pass into, and you can see that it refracts. The important thing to come away with, there's a certain angle that causes such a fast variation along that interface, it just can't exist in that second material. That concept's going to come up many times in this class. Is everybody good with that? Have you ever seen anything like that before? Does that help? Hurt? I don't know.
Makes me, for some odd reason, think of radar and materials to defeat it.
Good thinking. All right. Okay, everybody ready to move on? Okay, so now we can talk about critical angle and Brewster's angle and from a little bit more intelligent perspective. Get this stupid thing out of the way again. So boundary conditions require that that transverse component of the wave vector is continuous across the interface. That's what's going to force the field to look the same on either side. It's going to be varying just as abruptly. So the transverse component of K is continuous across the interface. So if that's the case, in fact, that transverse component of K is going to stay the same through your entire device. That doesn't ever change then. So when you build your model and you have something on a grid, that transverse component is going to stay the same, never changes throughout the entire device. Well, we know that the wave bends, so what's the thing that gives? It's actually the component of wave vector in that longitudinal direction, perpendicular to your interfaces, if you will. So how do we get that longitudinal component? We get it from the dispersion relation, right? Because inside a material, the magnitude of K is fixed. So we know one component, the transverse component, that's the same everywhere. So it's the longitudinal component that changes throughout your problem. And we calculate that from the dispersion relation. So for a two-dimensional material, here's a dispersion relation. And we'll say that we know Kx, because we know the wave coming in, and the x component is going to be the same everywhere. So we solve this equation for the longitudinal component, Ky. And so we get square root of the magnitude minus the x component squared. Well, this is where a very important thing happens. Now we have the square root of a difference. There's the potential that difference can go negative. And suddenly we have a complex longitudinal component, which we just drew some pictures of, by the way. So if that difference is positive, we have a purely real longitudinal component, and that means we're going to have a wave oscillate, and it's going to travel, it's going to keep pushing energy, right? If it's negative, we would actually say that the wave is cut off. When we have a negative inside that square root, we're going to have a purely imaginary component of the Ky vector. And there's just going to be pure decay in the direction away from that interface. No oscillations, so it's not going to push energy. It's just going to decay and eventually go to zero. Everybody good? So here's some pictures of that. So the first picture, we're going from something with a low index, stretched out wave, to something with high index, compressed wave. And there's always a way to match in that second medium, because we can always pick an angle that gives you a really long spatial period, but we can only go so short. So we can always match that, we always get transmission. The second picture is the opposite. Now we're going something from high index to low index. So there's this potential for a critical angle. But as long as we're not exceeding that, we get transmission in the second material. So the question is, what happens when it's cut off? Well, we actually do get a little bit of field on the other side of the interface, and a lot of times this is neglected in electromagnetic theory. It does penetrate, it's just cut off and decays. But there is actually energy on the other side of the interface. To throw some thermodynamics to this, that has to be the case. If there was no energy in the second material, it wouldn't feel the second material, and then it couldn't be cut off. So the only way it can totally internally reflect, it has to experience that material somehow, so it's got to penetrate into it. That make sense? And so the field on the other side looks like that. Remember, the transverse component is always real. It's continuous across the interface. So in terms of the x direction, we see waves. We see pure oscillation. But away from the interface, it's pure decay. So the field penetrates, but it's cut off. And that's actually what happens above the critical angle. And so there is actually a field on the other side of the interface. How is everybody with that? I'm a very visual person. I explain everything with pictures. All right, movie time. So let me play the movie. I think it should repeat. You know what? I'm doing two things at once. I'm recording my voice and trying to play a movie, and it appears PowerPoint melts trying to do. Okay, so this is just 4 freeze frames in those movies for the critical angle thing. Just below the critical angle, we still get transmission, but there's a huge field. Right above cutoff, which is at 45 degrees, we have a huge field penetrating into the second material. And if we backed up and we made it 45.1 degrees or something, that would get even larger. But as we get above and higher, it's more confined until we're just about at a real glancing angle. There's almost nothing going into that second material. But there always has to be something because it always has to experience it. And also because it penetrates, this is one reason why we're always going to have loss on a reflection. So if you make a mirror, metal is very lossy to light. And in order for it to reflect, it has to penetrate, and there's always going to be loss there. There's not really any way to get around that with a metal anyway. You can have dielectric stacks and get near 100% reflection, but with metals you're always going to have some kind of loss. Because even though the field's reflecting, and in theory should reflect 100%, it always penetrates and can experience whatever the loss is in that second material. Okay, everybody good? We can go quicker through this. If you had undergrad EMAG, you probably have seen this, but so we have, when we talk about reflection at interface, we already talked about the 2 polarizations, but we have 2 laws that help us figure out what happens. One is called Snell's law, and that just tells you the angle of the transmitted wave. Snell's law. Then we have what are called the Fresnel equations, and that's what tells us how much reflects and transmits. Have y'all seen these equations before, or is this new to everybody? Who's this new for? Okay, so y'all have seen it before. But what's interesting is what appears in these equations. So we're talking about the reflection and transmission for TE polarization. We see the material impedances are there. And we also see that the angles are there. So the amount that the wave gets reflected changes with angle of incidence. And you saw that from the movies. As we came in at a larger and larger angle, more and more reflected. So that appears in these equations. And also, the amount of reflection we get has to do with the change in impedances. If we had the same impedance on either side of the interface, there would be no reflections. So we can conclude that it's a change in impedance that really causes reflections. The deeper story behind that is why does a wave reflect at an interface? So remember, impedance describes a balance between the electric and magnetic fields. That's all it does. It's not any kind of density or anything. It's just a balance between them. The magnitude of impedance, if it's 3, then one of the fields is going to be 3 times smaller than the other. The angle talks about the phase. So you're going to have the electric field oscillating, you're going to have the magnetic field oscillating, and they're going to be out of phase. So impedance is just a balance between E and H. So your material 1 along comes with one certain balance. On the other side, they have to have a different balance. Yet the boundary conditions say that the E and H both have to be continuous across the interface. Yet impedance says, no, that balance is going to be different. Something's got to give. And so what gives is there's a reflected wave that can add to the applied wave to then get the boundary conditions to match. And that's actually the full story of why we get reflection. So anyway, those are the Fresnel equations and good for benchmarking codes. Everybody good? Okay. We can calculate the critical angle. You probably have all seen that before, so I don't need to get into that. But we can calculate critical angle. Brewster's angle, I pointed out, but I didn't really say it at the time, but there were certain circumstances where reflection went to 0 exactly. And this turns out as something called the Brewster's angle. So if the magnetic response on either side of the interface is the same, or there is no magnetic response, but then it would also be the same, there's no Brewster angle for the TE polarization. The TE polarization is always going to partially reflect or transmit unless there's some kind of magnetic response, which is on the rare side. That's not the case for the TM polarization. And in fact, we can make reflection go to 0. So this one completely transmits. This is useful actually for making polarizers. If we can get one of the polarizations to completely transmit, then that's what is going to get reflected. And we can get a purely polarized wave. And Brewster polarizers are reasonably common and they work really well. This is also why polarized sunglasses work. You have light that bounces off water, it gets partially polarized because the two modes reflect differently, and the TM polarization tends to transmit more than the other one, so you tend to get this one reflected more. So this is what is going to be reflected off the water, so if you block that, then you reduce glare, water or glass. So that's why polarized sunglasses work, because the reflection always tends to polarize a wave for that reason. Another interesting thing, let me ask you this question. So we have an interface, normal, comes at an angle, let's say that's 20 degrees. What's the angle of the reflected wave? So that's something that you're taught over and over and over, that the angle of reflection equals the angle of incidence. We're going to use it here too, but it's actually not true. It's only true when there's no loss and you have this plane wave of infinite extent, which none of those exist. So if you have a laser beam, for example, a laser beam is a confined wave, and we kind of think if we Fourier transform that, it's actually a bunch of waves at different angles. Well, we just saw through the Fresnel equation, waves at different angles reflect differently. So if you have a laser beam that hits an interface, when it reflects, it's going to be a lopsided Gaussian now. It's not going to be a nice Gaussian beam. The lopsided Gaussian is going to propagate at a slightly different angle. So if you're designing instrumentation and stuff like that, where that fraction of a degree is important, the angle of reflection is not the angle of incidence because of beams. And also, the wave doesn't leave at that exact point. Think of it more like this. Because the wave temporarily couples into this little evanescent field, and as that travels, it slowly leaks. So the wave actually exits the material slightly offset. Something else that's important if you're doing instrumentation that's accurate down to nanometers. So everything you've learned isn't true anymore.
Well, we just have one too many generalizations, right?
That's true. Too many simplifications. Actually, why I even got into numerical modeling. I'm very immature, and as you go through engineering, you always learn about these approximations. And if you assume that a horse is a sphere, you can do all these wonderful things. And those always bothered me. And the electromagnetics, they make a lot of them. Well, what if you don't make that approximation? So I got very interested in developing rigorous models to actually calculate things without making any approximations, to see what would happen. So that's actually one of the things that motivated me to get into this whole thing, and why we're going to see a lot of rigorous methods here, because I don't like the approximations. They bother me, and sometimes there's some really interesting things that can happen when you don't make those approximations. Although for the most part, the approximations are very, very good. Okay, onward. I'll skip that slide. You can go read that, but it's just summarizing everything we talked about. Okay, so we have two final quick topics, and then we'll break. Image theory. So let's say we're modeling some kind of crazy waveguide, or whatever that is. Notice the field has left-right symmetry, right? So that means the numbers over here are the same as the numbers over here, just reversed. And it also has up-down symmetry. So there's redundant information in this model. If somehow you know your answer is going to have that symmetry, it doesn't make sense to model this. We're going to model this, because there's just redundant information otherwise. So the ability to do this and how we handle those planes of symmetry is what's called image theory. And to summarize it, we can have two different kinds of interfaces where there's this symmetry. We can have perfect electric conductors and perfect magnetic conductors. And they're a little bit different. And later on, we'll see how to actually build those into models. But imagine you have a device here and two different fields on either side. If the normal components are oriented this way and the transverse components are opposite, and the magnetic fields have that symmetry, if your device would produce fields like that, you need to use a perfect electric conductor. Likewise, if the symmetry changes a little bit, you would need to use a perfect magnetic conductor. This is really, really common in modeling where there's this left, right, up, down redundancy. You slice a plane through the middle of it and you choose perfect electric or perfect magnetic, just depending on what kind of fields the device would actually produce. Unfortunately, we're not going to implement that in this class. That's why I'm not going into a lot of detail, but keep that in mind because that can really, really improve the efficiency of your model. It isn't too bad. You know, maybe you could do that as a project. You could compare doing a full simulation versus doing a simulation with it being much reduced. So that's it. That's image theory. That's all it really is. Other than this cool picture I found on Google. So that's modeling probably some kind of field around an airplane, but guess what they're doing here? They're using some kind of image plane. Perfect electric, perfect magnetic, I don't know. But think of how much smaller that is. It's half the size, and you're missing nothing, no information. Everything's there.
It's structural.
It might be a structural model. It was a cool picture, and
It is very
helped me
cool.
talk through it. So
Beautiful.
could be a thermal
Beautiful
model. It has
colors.
nothing to do with electromagnetics. I don't know. I just stole the picture.
Interesting they're using triangular grids.
Yes. So it's looks like some kind of boundary element method that they're doing. Okay, last topic, lenses. So clearly lenses either focus or diverge waves. This is useful because sometimes you're going to want to source a device with some kind of beam, and you're going to want to control whether it's converging or diverging. So just knowing the basics on some lenses is very helpful. Ray tracing. This is the way that you can trace a ray through a lens to figure out where it's going to focus, where your image is going to be, etc. So we have some definitions. We're going to use what's called the thin lens approximation. And this is pretty good because when we build lenses into our models, we can make them thin because we don't really care that it's a lens. We're just probably trying to create some kind of beam to hit the thing we actually want to model. So we can use thin lens. Where all the waves focus, we'll call the focal point. And then the plane where that happens, we call the focal plane. And then, of course, the axis running through this. Where's my laser pointer? There it is. So the axis running through this whole thing is called the optical axis. That runs right down the center of the lens. All right, rule number 1 for ray tracing. If a ray enters the lens at its center, it just goes straight. It's unaffected by the lens. If a ray enters the lens parallel to the optical axis, it passes through the focal point. In fact, you don't even need this rule. You can just get away with rules 1 and 3 because this is a combination of those. But it's useful to know. And rule number 3, for an arbitrary wave at some angle, if you draw something parallel to it that passes through the center of the lens, those two rays will pass through the same point in the focal plane. So really just rules 1 and 3 can predict rule number 2, but that's the basic rules of ray tracing. So if you're trying to control a beam hitting an object, these are the types of things that you consider. We're not going to do it in this class, but I wanted to point it out because it is used a lot to shape beams that interrogate something. If you want to design a lens to produce a particular curvature or place a focal point at a particular place, there's what's called the lens maker equation. So you can pick your radiuses on either side of the lens and design its focal length to do whatever you want it to. So Won't do it in this class, but I just want you aware of that. And the last thing that isn't in your slides that I wanted to share with you, but it's kind of cool, there's a new building in London that has a nice little concave shape. And this time of year, where the sun's up here, it actually beams and focuses down on the ground, and it melted some guy's Jaguar. It made the news. So lensing is a real thing. I hate to be sitting there. It'd probably be very hot. But all right, so lenses are real. I'm going to leave you with that. We'll break for, I don't know, 5-10 minutes.
I can just imagine the sunburn.
Yeah.
That somebody would, yeah.
I'd rather get a sunburn than burn my Jaguar. My Jaguar is more important than my life.